Hello, geometry students. In this lesson, in our 5.4 notes, we're going to learn a new way to write a proof called an indirect proof. So first of all, I want you to know that indirect proof is also called proof by contradiction. So let's take a look at an example of how we can prove something indirectly by contradiction. So imagine this scenario. Suppose that you bought 2 t-shirts and spent over $40 excluding tax. You lost the receipt, so you don't remember the cost of each t-shirt. Your friend thinks that both t-shirts cost less than $20. So finishing, oops, looks like that's a typo there, sorry. Should just say finish. So finish writing an argument below to prove to your friend that at least one shirt must have cost more than $20. All right, so you know you spent more than $40. Your friend thinks that that both t-shirts cost less than $20. So we're going to write an argument below to prove to your friend that at least one shirt must have cost more than $20. So we'll start it like this. Suppose both t-shirts did cost less than $20. So let's assume what your friend is saying is true. Then we could finish the argument like this. We could say, well, then the total, if both t-shirts cost less than $20, then the total that you spent would be less than $40. Now, the problem with that is that this contradicts what you know to be true. This contradicts the fact that you spent more than $40. All right? So since assuming that both t-shirts cost less than $20 contradicts a known fact, then you finish up your argument by saying, therefore, it must be true. Therefore, it must be true that at least one t-shirt cost more than $20. That at least one t-shirt, oops, I'm running out of space here, cost more than $20. All right, so let's take a look at the steps that we'll follow when we write an indirect proof. So we'll follow these steps to write an indirect proof. Number one, we're going to assume the negation of the proof statement. We're going to assume that that negation of the proof statement is actually true. So we'll assume the negation of the proof statement to be true. The second thing we'll do is that we'll use logical reasoning, the same kind of reasoning skills we use in a direct proof, to show that your assumption contradicts all or part of the hypothesis. Now remember where you get the hypothesis. The hypothesis is the given information. All right? And then step 3, we will just state the following. And I'm going to give you kind of a template here to follow. We'll say the following. Since assuming the negation of the conclusion, now remember that conclusion is your proof statement. Since assuming the negation of the proof statement contradicts the hypothesis, the given statement, you finish up by saying, then it must be true that whatever the proof statement was is actually true. So we'll look at an example here in just a second, but we can kind of see in our t-shirt example what happened. We assume the negation of the proof statement. We want to prove that at least one shirt cost more than $20. So we negated that. We said, suppose both t-shirt cost less than $20. Then we showed that that led to a contradiction of a fact that we knew to be true. We knew that we had spent more than $40. So therefore, we can say that since assuming that both t-shirts cost less than $20 contradicted what we knew to be true, that we spent more than $40, then it must be true that at least one t-shirt cost more than $20. So we'll look at a few examples of writing proofs in just a second, but I want to kind of tell you what the logic is that allows these indirect proofs to work. And it goes back to what we learned at the beginning or early in the semester when we were learning about conditional statements. A conditional statement looks like this, and it's contrapositive. Remember, the contrapositive of a conditional statement is when we negate both the hypothesis and the conclusion, and we switch them. So a contrapositive would look like this. Not Q implies not P. And what you'll remember from early in the semester is that we learned that a conditional statement and its converse are what we call logically equivalent. So let's see if I can squeeze that in there. Okay, logically equivalent. So let's review what that means. What that means is that both a conditional statement and its contrapositive, they're either both true or they're both false. So if one is true, the other is true. If one is false, the other is false. So, in other words, if not Q implies not P, if that's a true statement, if a contrapositive is true, then by law of logic and the fact that a contrapositive and a conditional are logically equivalent, it's going to be true that P implies Q. So in other words, if we assume the negation of the conclusion of our proof statement and show that that leads to a contradiction of the hypothesis, then it must be true that the original hypothesis implies the original conclusion. So let's take a look at some examples of actually writing some indirect proofs. And we'll look at different types of proofs or different types of scenarios. Let's start with an indirect proof that involves some algebra. So this first one's, we're going to assume that negative 3x plus 4 is greater than 16. What we're going to prove is that x is less than negative 4. All right, so it's a three-step process. If you look up at your notes, step number 1 said, assume the negation of the proof statement. So the negation of x is less than negative 4 is to say x is not less than negative 4. So what that means is we're going to assume that x is greater than or equal to negative 4. That would be the negation of x less than negative 4. If we're going to say x is not less than negative 4, then that means x would have to be greater than or equal to negative 4. So let's take a look at what would happen if x actually were a number that was greater than or equal to negative 4. So let's start with if x were actually equal to negative 4. Then negative 3 times negative 4 plus 4. All I'm doing is I'm just taking a negative 4, I'm putting it in here for x. And negative 3 times negative 4 plus 4 would be 12 plus 4, which equals 16. So that contradicts the given. Remember, the given said that negative 3x plus 4 should be greater than 16. Well, what about the other case? We've talked about if x were equal to negative 4. What if x were a number that's bigger than negative 4? So let's pick a number that's bigger than negative 4, like negative 3, and see what happens. So we would take negative 3, multiply it by negative 4 plus 4. Again, all I'm doing is I'm taking negative... Oops, I meant to put negative 3. Let me fix that. Sorry about that. We're going to take negative 3 times negative 3. What I did is I picked a number that's bigger than negative 4. Negative 3 is to the right of negative 4 on the number line, so it's bigger. I'm putting it in for x, and I'm evaluating. Negative 3 times negative 3 plus 4 would be, let's see, 9 plus 4, that would be 13. So we can see that in either case, taking a number that's either equal to negative 4 or a number that's bigger than negative 4, if we put it in for x, we see that that's a contradiction of the given statement of our hypothesis. Remember, negative 3x plus 4 should be bigger than 16. We got a number that was either equal to 16 or less than 16. So we can say that this contradicts the given. It contradicts the fact that 3 times x plus 4 should be bigger than 16. All right, so now we're ready to make our conclusion. So follow that template that I showed you up here. We're going to say, since assuming the negation of our conclusion, which in this case, we assume that x is greater than negative 4. So since assuming, you'll say those words in every indirect proof. Let me just underline that. since assuming what? What did we assume? That x was greater than or equal to -4, okay? Since that contradicts our given, okay, that contradicts our given, which was that -3x plus 4 should be greater than 16, comma. We'll finish up by saying, then, oops, I'm right there in blue, sorry. Then it must be true, that, now we'll go ahead and write our original proof statement. Our original proof statement was that x is less than -4. It must be true that x is less than -4. Okay, so let me just kind of highlight what happened here. So in every indirect proof, we'll state the same thing. We'll say since assuming, and then we'll put what our assumption was. Oops, I have a typo there, don't I? I left out the negative sign. Sorry about that. So since assuming that x is greater than equal to -4, then we'll say contradicts and put your given statement here. Then finish up with the phrase, then it must be true that x is less than -4. That was our original proof statement, all right? So again, just follow the same template. You'll say since assuming every time, have contradicts in the middle, and then say then it must be true that. And so let me just kind of fill in. This will be your assumption, the negation of your proof statement. This will be what it contradicts, and then you'll say, finish it off with what you actually wanted to prove. So now let's write an indirect proof that has to do with some number theory. So let's say we're given the following. Given that x plus 2 is an even integer, let's prove that x must also be an even integer. All right, so to prove this indirectly, step 1, remember, is to assume the negation of your proof statement. So our proof statement is that x is an even integer. So to negate that, we'll just say that x is not an even integer. So we are going to assume that x is not an even integer. Okay? Well, if that were the case, picture a number line in your mind, if you would. If x is not an even integer, then x plus 2, that means it's odd, then x plus 2 would have to be odd. Then x plus 2 is odd. Again, let's just picture a number line, okay? Let's say here's 0, here's 1, here's 2, here's 3. So let's take an odd number. So assuming that x is not an even integer, so let's pick one that's not even, like 1, 1 is odd. Then if I add 2 to that, I'm going to get to the next odd integer. Okay, so we've already gotten to our contradiction. That contradicts the given statement, our hypothesis that x plus 2 is even. So we'll finish off our indirect proof by saying the following. Since assuming, what did we assume? That x is not even. Okay, since assuming that x is not even contradicted something, what did it contradict? It contradicts the fact that, x plus 2 is an even integer. X plus 2 is an even integer. Okay, comma. Then we'll finish it up with the phrase, then it must be true that our original proof statement has to be true. Our original proof statement was that, that x is an even integer. So it must be true that x is an even integer. All right? I can't spell. Integer. That's an E right there. Okay, so let's just kind of review what happened. What did we assume? We assumed the negation of the proof statement. We assumed that x was not an even integer. Well, if x is not an even integer, then that immediately leads to a contradiction. X plus 2 would have to be odd. We showed that with the number line. Well, since assuming that x is not even contradicts the given that x plus 2 must be even, then we finish it off by saying that it must be true that x is an even integer. So again, you'll just follow the same template in every one of these indirect proofs. So now let's take a look at a real-world example of an indirect proof, kind of like the t-shirt example. Suppose we are given that we took a trip of over 360 miles with 2 stops. All right, so this is what we're assuming to be true, that the trip was more than 360 miles and we stopped twice. So let's kind of draw a picture of what that would look like. If I'm going to have 2 stops, here's my beginning point. I have a stop and then another stop and then I have an ending point. So in other words, this trip would have 1, 2, 3 legs to it, okay? So assuming that a trip of over 360 miles has 2 stops, let's prove that one leg of the trip had to be more than 120. All right, so to prove this indirectly, step 1, remember, is to assume the negation of the proof statement. So our proof statement is that one leg of the trip was more than 120 miles. So negate that, we would say that one leg of the trip was not more than 120 miles. All right, so what we need to assume then is we need to assume that every leg of the trip, every leg was, I'm going to say, less than or equal to 120 miles. Okay, well, if that's the case, if that were true, if I have these 3 legs and they're all less than 120 miles, that means the total of these 3 parts of the trip would be less than 360. That's where we find our contradiction. Then if that were the case, the total distance that we traveled, the total distance would be less than or equal to 360 miles. So that's our contradiction, because remember, we assumed that the trip was over 360 miles. So since we've reached our contradiction, we're ready to finish up the indirect proof. So we'll say that since assuming that one leg of the trip was less than or equal to 120 miles contradicts the given. What was the given? The given was that contradicts that the total trip was greater than 360 miles. Then we're ready to say, then it must be true then it must be true that what must be true? The original proof statement, that one leg of the trip was more than 120 miles. That one leg was more than 120 miles. Okay, so I hope you see that same template again. Since assuming that one leg was less than or equal to 120 miles contradicts, oops, let me do that with a red pen, contradicts the fact that the total trip was greater than 360 miles, then we finish up by saying, then it must be true that one leg was more than 120 miles. All right, so now we're ready to look at some actual geometric proofs. Okay, before we do this next proof, I want you to flip your paper over. So flip it over and look at the steps for an indirect proof. And I want you to look at step number 2. where it says, use logical reasoning to show that your assumption contradicts all or part of the hypothesis, but then it goes on to say, or contradicts some other fact, such as a definition, a postulate, a theorem, or a corollary. That's what's going to happen in this proof. We're going to show that the contradiction isn't necessarily the specific information, the hypothesis, but it's going to be a contradiction of some other established fact, like a definition, postulate, theorem, or corollary. Okay, so flip your paper back over then, and let's take a look at this first geometric indirect proof. This is going to be a proof of a theorem that we talked about last time in class called the exterior angle inequality theorem, which says anytime we have an exterior angle like this angle 4, the measure of that angle will be bigger than either of the remote interior angles. So in other words, the measure of angle 4 is greater than the measure of angle 1, and the measure of angle 4 is greater than the measure of angle 2. So that's what we're given here. 4 is an exterior angle of triangle ABC. We're going to prove that the measure of angle 4 is greater than both of those or either of those remote interior angles. Okay, but we're going to follow the same 3 steps that we did in the other proofs. So step 1 is to assume the negation of the proof statement. So to negate the fact that the measure of angle 1 is greater than the measure of angle, the measure of angle 4 is greater than the measure of angle 1, we say the measure of angle 4 is not greater than the measure of angle 1. In other words, we'll say that the measure of angle 4, we're going to assume that the measure of angle 4 is less than or equal to the measure of angle 1, and that the measure of angle 4 is less than or equal to the measure of angle 2. Okay, well, if that were the case, if we assume that to be true, then in step number 2, what that means then is that the sum of the measure of angle 1 and the measure of angle 2, now let's think about this. If we're assuming that the measure of angle 1 is less than the measure of angle 4 is less than the measure of angle 1, we could turn that around and say the measure of angle 1 is greater than the measure of angle 4. And the measure of angle 2 is greater than the measure of angle 4. So if both 1 and 2 have measures greater than the angle 4, than the measure of angle 4, then their sum would be greater than the measure of angle 4. Now, that reaches a contradiction, because let's think about what we know about exterior angles. Remember, we have proved in the past the exterior angle theorem that says the measure of an exterior angle should be equal to the sum of the remote interior angles. So we've already reached our contradiction. We can say that this assumption would contradicts a known fact, which is the exterior angle theorem, which says the measure of the exterior angle should be equal to the sum of the two remote interior angles. So once you reach your contradiction, then you're ready to finish it off with step 3. So in step 3, we're going to say that since assuming, what did we assume? We assumed that the measure of angle 4 was less than or equal to the measure of angle 1, and the measure of angle 4 was less than or equal to the measure of angle 2. Since assuming that contradicts something, in this case it didn't contradict the given, it contradicts the exterior angle theorem, then we can finish off and say, then it must be true that, what was our original hypothesis, or our original proof statement? That the measure of angle 1 is greater than the measure, keep saying that backwards. The measure of angle 4 is greater than the measure of angle 1, and the measure of angle 4 is greater than the measure of angle 2. So we'll finish that off by saying that the measure of angle 4 is greater than the measure of angle 1, and the measure of angle 4 is greater than the measure of angle 2. All right, so we had the same template. Since assuming the negation of the proof statement contradicted something, in this case it contradicted a known fact, then we can finish it off and say then it must be true that the original proof statement has to be true, that the measure of angle 4 is greater than the measure of angle 1, and the measure of angle 4 is greater than the measure of angle 2. Okay, I want you to see one more example where in this case it's going to take us a little more work, a few extra steps to actually reach our contradiction. So in this example, we're given that MO is congruent to ON and that NP, this segment, is not congruent to NP. And then we're going to prove that angle 1 is not congruent to angle 2. Now remember, if you flip your paper back over and look at those steps, we only need to reach a contradiction of part of the hypothesis, and that's what's going to happen in this case. All right, so step 1, we're going to assume the negation of the proof statement. So the proof statement is that angle 1 is not congruent to angle 2. Well, to negate a statement that has a not in it, you take the not away. So we are going to assume that angle 1 is congruent to angle 2. All right, then step 2, let's think about how this is going to lead us to a contradiction. So we're going to assume that angle 1 is congruent to angle 2, okay? Also, we're given that MO is congruent to ON, and also we can see that these two triangles share a side, share OP. So what that's going to mean, if that were true, if we assume that angle 1 is congruent to angle 2, and we have these pair of sides congruent and the side they share, these two triangles would be congruent by side, angle, side, okay? Which leads to our contradiction, because if the two angles were congruent, then side MP would have to be congruent to side PN by CPCTC, and that contradicts this part of the given. So once we reach that contradiction, we're done. Okay, so let's go ahead and write down what we just talked about. So we're assuming that angle 1 is congruent to angle 2. So let me just kind of do this. So we'll have an angle congruent, okay? Then in step 2, we're going to say, then since MO is congruent to ON, and I'm just going to justify that. I'm going to put justification in parentheses. That was given. We assume that to be true. That's another side. And since OP is congruent to itself, and let's justify that with the reflexive property of congruence, okay? Then triangle, let's see. Let me mark, that was my second side. So we have two sides and one angle. We can see from the picture, let me mark that OP congruent to itself. We can see from the picture that the angle, we've got two sides and an angle. The angle is the included angle. So that's enough to justify that the two triangles are congruent. So we can say that triangle MOP would be congruent to triangle NOP, okay? And let's justify that. The reason would be because side angle side implies congruent triangles, okay? And if that's true, then angle 1 would have to be congruent to angle 2 because of CPCTC. Okay, so that's our contradiction. We have reached the contradiction. Remember, you only have to find a contradiction of part of the given. I'm sorry. It's not that angle 1 is congruent to angle 2. Let me fix that. Okay, so once we get the two triangles congruent, then we can say that MP is congruent to NP because of CPCTC. So MP is congruent to NP, and our reason is CPCTC. Okay, so that's our contradiction. We've reached a contradiction. So we're ready then to finish off this proof. We can say that since assuming, that angle 1 is congruent to angle 2, angle 1 is congruent to angle 2, contradicts something. It contradicts the fact that we were assuming, or assuming means we are saying it's true, that segment MP was not congruent to NP. Remember what our assumption led to? It led to this conclusion, that they would have to be congruent. So since that assumption that 1 is congruent to 2 contradicts the given that NP is not congruent to NP, then we'll finish it off and say, then it must be true that the original proof statement. The original proof statement is that angle 1 is not congruent to angle 2. Angle 1 is not congruent to angle 2. Okay, so there you go. You have some examples to look at. Go ahead and get started on your homework. Do as much as you can. And then when I see you in class next time, I'll give you plenty of help if you need it writing the indirect proofs on your homework. So I wish you the best of luck.